So we're going to continue. This is the last of our lectures for the course. And you guys are the only ones who are going to get attendance. I was not joking. So can we get a piece of paper and take all of their names? Just pass it around, please. Put in your names and your Android IDs, right? I get to pick. Yes, you're good. Okay, so here was the problem. We're going to continue with Kalman filtering. The problem was this: you were given a state space system where there was an underlying state that this process followed, and this was an evolving state. The state was assumed to be Markovian in the sense that the state at time t only depended on the state at time t-1, and they had some random perturbation to it. Then you had an observation where the observation at time t depended only on the state at time t. And from the sequence of observations, we had to determine the underlying state of the system. There were many applications for this: controls, autonomous vehicles, robots, spacecraft, missiles, the whole lot. All of them basically use this mechanism, right? And of course, even if you're predicting the stock market, anything of that kind, you're still going to be using this mechanism. So this is basically fundamental to so many things that you encounter in day-to-day life. And so here is how the estimation process went. You start off, you had a best guess for the state at time t-1, or we can say the best guess for the state at the current time. And using the state at the current time, you guessed and the state transition relationship. You predicted the state at the next time. So from s hat t-1, you predicted s bar of t, which is the predicted state at time t. And then from the predicted state, you predicted the next observation. So now you moved on to time t, you have a predicted state, and then you have predicted an observation. And then you make an actual observation. There's a difference between the predicted observation and the actual observation, which means that your estimate for the state was wrong, right? And so you're going to correct your estimate for the state by a factor that is linearly proportional to the difference between the actual observation that you make and the observation that you predict. And the scaling factor, what do we call this? The Kalman gain, right? Very simple. And so this was the basic idea. This is how we did it. You predicted the state at time t, and then based on the new observation, you updated your state. Yes.
The state is the set of what it was.
The predicted state is the wind velocity.
Oh, yeah.
No, the observation is so you're shooting at the center point of the okay, in this case the predicted state is going to be the Gaussian distribution. So it's, remember the kidnapping story, right? The predicted state is what you think the car is going to be doing at the next time.
So that would be like my Gaussian distribution. It's a point.
It's a point on one of the axes. The Gaussian distribution is multidimensional, right? What are the axes of your Gaussian distribution? If it's observation and state, then the state is going to be some point on the x-axis, the observations along the y, right? Yeah. Thank you very, very much, man. Truly appreciate it. I have a sore throat. Probably going to fall sick after the semester is over, so the hot coffee helps. All right. So this was, everybody remember this? Okay. And you can also, so in the process, what are we doing? We're predicting the next observation, right? We're predicting the next observation and looking at the difference between the predicted and the true observations. And so you actually have a way of predicting the next observation. Now observe that you're not using the next, if you had to predict the observation 10 time steps out, you would not be using you would not be making a chain of predictions of observations. You'd be making a chain of predictions of states. And at the time at which you want to predict the observation, you're going to use the state value to predict the observation. That's the way you go about it, right? So now, anyway, just the math on the board. So we saw this difference between the discrete time and the continuous time case. Now, this is something that we're going to have to revisit later in today's lecture. So I will point this difference out again. If you have a belief in the state at the current time, then the belief in any state at the next time, if you're using the discrete state system, is that the state at time t, the probability of being in any state at time t is the probability of being in any state at time t minus 1 and transitioning from here to the next state. And you'd be summing over all states at time t minus 1. That's the discrete state version. The continuous state version, you're going to be integrating over all possible states at time t minus 1 and then factoring in how you would transition from that state to the target state, right? And so this gave us the predicted belief in the state at time t, given all observations. And then when you got the latest observation, you factored that in. And how did you factor it in? You just multiplied the prior belief in the state by the probability of the observation given the state and normalized it. So it was a distribution, right? And this was a distribution over the state. So this is what, these were the two equations we went through in the past two classes. Everybody remember this? Right. Then for the continuous case state system, we also had we started off with this very simple case where the equations were linear. So the dynamics of the state were linear, meaning the state at any time t was a linear function of the state at time t minus 1 plus some perturbation, a noise. And the observation at time t was a linear function of the state at time t plus some perturbation, which was the noise. And we assumed that the noise was Gaussian in all cases. We also assumed that the initial probability distribution of the state was Gaussian, right? We saw one example. This was the wind and the target toy example, where the wind velocity might keep changing all the time, but the wind velocity is a state which has a dynamic, meaning the state at time t is going to be a function, is the wind velocity at any time is going to, your best guess for the wind velocity at any time is that it's going to be the same as the previous time, but it will change. And the perturbation has a Gaussian distribution. The observation at any time is going to be a linear function of the wind velocity, right? And there will be a perturbation, which is your observation noise, right? And so based on observations, you had to predict the wind velocity. And from these equations, we came up with the Kalman filtering equation. The Kalman filtering equation had two components. What were these two components? Anybody? What were the two stages of the Kalman filtering process? You wanted to predict the state at the next time. And then from the predicted state, you predicted the observation, you found a correction, you made an actual observation, you made a correction, right? So what are the top two equations? Can anybody explain? Remind me what those top two equations are? Pardon me? So you have some s hat t minus 1 is the predicted state at time t minus 1. And if you just plug that into the state dynamics equation, you're going to get the prediction for the state at time t, right? And then if the state at time t minus 1 has some uncertainty, r hat t minus 1, then the uncertainty at time t is going to be a times r hat t minus 1 times a transpose plus the variance of the noise, right? That's just the prediction. Then you made an observation, O, and you had a predicted observation, O bar. And so the predicted observation is simply going to be B times S bar plus the mean of gamma, correct? And the actual observation is going to be OT. So this difference, this term here, is the error between the predicted observation and the actual observation. And you're going to correct your state by a factor, by a scaling, by a scaled version of the error in the observation. And because now you have made a correction, your uncertainty in the state has gone down, right? And the uncertainty in the state, if it was RT before you made the observation, after you made the observation, you shrank it by multiplying it by a factor I minus AB, right? So that everybody remembers all of this. There's nothing magical. You could actually sort of pull this out of your hat in any time, right? The only magical term over here was what the Kalman gain itself was. And the Kalman gain, that's the only term over there which comes out of, which sort of comes out of the blue in some sense, right? And this again is just derived on the maximum a posteriori estimate of the Gaussian distribution of yeah, this is going to be CYX times CXX inverse. That's the Kalman gain, right? So everybody remembers this, correct? In this case, it's going to be CSO times CO inverse. CO is the observation variance, right? So this, is everybody comfortable with this idea? This derivation, right? Nothing fancy. And it all makes sense, mathematical sense. We are not going through any complicated mathematics for this. But then that and the Kalman filter made a couple of key assumptions. What were the assumptions? Linear system, yes, and Gaussian. Everything was Gaussian and the system was linear. So F was Gaussian, F was linear, G was linear, epsilon and gamma were Gaussian. These assumptions can fail, correct? So how do you deal with it when these assumptions fail? That's what today's class is going to be about. Let's look at the first case. F and or G may not be nice linear functions. So conventional Kalman update rules are no longer valid. Why are they no longer valid? So the Kalman update rules, to understand why they're not valid, we have to go back and look at where the formulae came from. So the formulae said that the probability of the state at time t, given all observations until t minus 1, was p of st given p of st minus 1, p times p of st given st minus 1 integrated over st minus 1, right? So now if you look at the state equation over there, that state equation, both of those terms may be ugly, right? So every one of these update rules can actually be ugly and end up being intractable. So the specific reason for this is that, for instance, even if I give you the state and I ask you what is the probability of the observation given the state, and if the relationship between the state and the observation is some nonlinear function g, then the probability distribution of the observation given the state is going to invoke Jacobians of this function and ugly terms which you don't really want to deal with, right? I could spend half an hour explaining how that equation on this board came about. But the fact of the matter is our life would be better off if we didn't have to deal with it. So we're not going to deal with it. Okay. But just to give you an idea of how this thing complicates matters, I'm going to consider a specific form of nonlinearity. Instead of saying g of s comma epsilon, I'm going to say g of s plus epsilon. I can always think of a stochastic function as a deterministic function plus noise, right? So I'm going to say that the function O is some g of s plus gamma, and st is going to be some other f of st minus 1 plus gamma, right? So all the noise is additive, okay? So now consider this case. O equals gamma plus log of 1 plus x of s. This is actually a pretty nice linear function if you really think about it, right? It's linear to the right, that's linear to the left. Unfortunately, it has a bend in the middle. And so what is if gamma is Gaussian, what is P of O given gamma? If P of O given is P of O given S, if S is given, that term log of 1 plus x of s is not is a given term, right? So the probability distribution of O given S is simply going to be the probability distribution of gamma with the mean shifted to by log of 1 plus x perf x, right? X perf s. And so the probability of the observation given S is simply going to be the same as the distribution for gamma. The mean mu gamma has been shifted by this amount, and the variance is the same as the variance of gamma, right? And let's look at what happens when I stick this into making my updated distribution P of S given O. And we very quickly see that if I look at this as a function of S, it's not Gaussian. There's some ugly shape. It has an exponential form, but it's not Gaussian. I've plotted the shape to the right, and it's not a symmetric curve. In case you can make out, it's slightly skewed, right? And so and now for the state, let's assume I still have a linear equation, right? So the only nonlinearity I have is in the observation. And this we saw in the case of the vehicles, for instance, we saw this is a common enough situation. The state can always be expressed as a linear equation, but the observations are going to be a nonlinear function of the state. So this is a very common situation. And we find that if I look at the predicted probability of distribution of the state given the observation, it's going to be intractable. If I look at every single step becomes intractable. I'm not going to spend any time explaining these equations. You just have to take my word for it. If you're so inclined, if you're masochistic, you can put pen on paper, you can work it out. It'll take you 5 or 10 minutes to get each of these equations. And well, it's not going to be tractable, right? Okay, so now we have this problem. Nonlinearity killed us. We know how to deal with linear functions. So what can we do? We can linearize, right? But how do we justify linearization? What do we mean by linearizing? So let me go back and look at this function, log of 1 plus x perf s. Okay? At any point, the tangent is a line. So I can say I'm going to approximate that blue curve by the red curve. But where do I draw that red curve? Where do I draw the red line? What is the tangent point? Which tangent point do I choose? So at any point time, this is just the relationship between the observation and the state, correct? Or maybe the next state and the current state. But I currently have a probability distribution for the state at every time, right? And that distribution is going to have a mean and it's going to have a variance. Is the distribution going to be broad? Very likely not, right? And how do these distributions typically look? They have a mode around the mean, and then they fall off rapidly. They have to fall off, otherwise the area is not going to be 1, right? So look at that. If at every point, the tangent is a good local approximation. What do I mean by a local approximation? At this point, around the region where I made the linearization, around which I've linearized the function, the error between the blue curve and the red curve is very small. It's only when you go further away that the error becomes large, right? But then I also have, and this is going to be true regardless of where I draw it. These are all the linearizations. Now, here's the other thing that comes to our aid. Is there a chalk here? Yeah, there is. And this also tells us where we're going to have to linearize our function. Okay. So let's say I have this is my real function, right? And let's say that the probability distribution for the state at the current time, whether it's the predicted state or the corrected distribution after you have actually observed the observation, is something like this. Where do you want to linearize? Yes. At the mean. Why?
Most likely the point of the grass.
You want to linear. So here's the thing. If I linearize, I want to linearize near the mode, not the mean. Because at the most probable location, I want the error to be small. Right? In the case of Gaussians, the mode and mean are the same. And so what will happen is that although the error increases pretty dramatically as you go further away, the probability falls off exponentially fast as you go further away. So in this region where most of the probability mass lies, the error is going to be small. That makes sense? Right? And this, I can take advantage of this. That in the region, if I choose the correct point to linearize, then the cumulated error over the entire state space is actually going to be quite small. Make sense? Right? And so that's what I'm going to do. Now, how do you linearize a function? Anybody? Taylor series, but these are vectors. So how do you linearize a function? How do you linearize a vector function? You would use a Jacobian, right? So if I've got any function, if I have a function st or O equals some f of s plus epsilon, right? Then if I want to linearize around some point s bar, then I'm going to say O is approximated as f of s bar plus what? The Jacobian of s, f with respect to s, times s minus s bar plus epsilon. Right? This is your standard linearization function. And so I can just write it like that. That's gamma. In this case, O equals gamma plus g of s. I can write it as gamma plus g at s bar plus the Jacobian times the difference. How far away you are from the mean. Okay. This makes sense to everybody? Right. Okay. You are making the expansion around the current predicted a priori or whatever mean of the state, the mode actually, right? And typically, if you're making Gaussian assumptions for gamma, then we will find that the distributions is stay Gaussian all along, right? And so the probability of S is small where the approximation error is going to be large, and where the approximation error is small, the probability is large. So this works out. So this was for the observation equation. I can do the same thing for the state equation, right? If the state equation is nonlinear, typically state equations will not be nonlinear. But if the state equation is nonlinear, I can make the same linearization. I can linearize the state equation around the current mean, right? And if I linearize the state equation around the current mean, then once again, this is going to be st, it is going to be epsilon plus f of s hat t minus 1. S hat t minus 1 is the mean of the state at time t minus 1, right? Plus the Jacobian of the function f times st minus 1 minus s hat t minus 1. This is just your the first order term. Everybody fine with these equations? Okay. So how is this going to affect our life? It turns out once you decide that linearization just makes sense, then here's what happened. You had O equals gamma plus g of s. Again, it's typically g of s comma gamma, but then as I explained, I can always write it as the sum of a deterministic component and a noise, right? And so also st equals f of st minus 1 plus epsilon. I've written it as a deterministic function plus some noise. And so when I linearize it, I'm going to get O equals gamma plus g of s bar times the Jacobian times s minus s bar. And st equals epsilon plus f of s hat, which is the point at which I've chosen to linearize, times Jacobian times st minus 1 minus st minus 1 hat. Again, the hats and bars are kind of not really key over here. The fact is we are expanding around a mean, right? They become relevant once we begin talking about the extended Kalman filter. So the extended Kalman filter is basically just a Kalman filter where the functions f and g are no longer linear. And so the functions f and g are no longer linear, then we're going to linearize them. But where do we linearize them? It turns out, remember, in a Kalman filter, we make two kinds of predictions. What are the predictions we're making? We're predicting the state at the next time, and we're predicting the observation from the state, right? And so for these, do I really need any linearization? It's a nice functional form. These are not statistical terms. I can predict the state. I can predict the observation. I don't need to worry about linearization. Linearization is only required when I'm beginning to compute statistical variables. In this case, what is the statistical variable over here? You were saying? The variance, right? The uncertainty. That's the only statistical variable over here, correct? Make sense? And so here's what I can do. Let's say I have my best guess for the state at time t minus 1, which is s hat t minus 1. What is my best guess for the state at time t? It's going to be f of s hat t minus 1 plus the mean of the noise. I'm assuming the noise is zero mean for now, right? If the noise is not zero mean, you guys will know exactly how to deal with this over here, because there's nothing magical going on. Everybody with me? Right? So have we done any linearization over here? No, I literally just plugged it into my state transition or state dynamics equation, correct? And then I have to compute the updated uncertainty. So let's say the uncertainty at time t minus 1, my best guess was r hat of t minus 1. Then at this point, this is where I'm going to have to linearize, okay? And when I linearize, I made this a linear equation. And then if you go back and look at the linear equation I had out back here, observe, this is simply the form of constant plus a times s, right? Or constant plus b times s. What are a and b? The Jacobians, right? Make sense? Okay. And so I'm just going to be saying that a out here, this is going to be the Jacobian of the function, state transition function. And so I'll just be multiplying. The uncertainty is going to be the uncertainty of the noise plus the uncertainty of the state at time t minus 1 pre and post multiplied by a and a transpose, where a is the Jacobian of the transition equation. And the Jacobian simply becomes the matrix multiplier for the linear equation, right? Everybody with me? Right, nothing magical happened. And then if I'm predicting my observation at the next time, what am I going to do? Anyone? How do I predict the observation at the next time? Can someone speak up? G of what? S, which S? ST, S bar T. Right. Correct. That makes sense because you predicted the state. The state was S bar of T. So I'm going to put the predicted state through my equation, right? And so the predicted observation is now going to be okay. The predicted observation is now going to be simply G of S bar of T. Now, this is making an assumption. What is that? What is the assumption I'm making here? Guys, what assumption am I making? Yeah? Pardon me? Zero mean for gamma, right? If the gamma were not zero mean, then what would this equation be? Plus mean of gamma. That's it. That's the expectation there, right? Easy. And so I have made my prediction for my observation. And then the true observation is going to be OT minus the predicted observation, right? And now I'm actually going to need the Kalman gain. And for computing the Kalman gain, I'm going to have to linearize. This is the only place where I'm actually going to have to linearize. And when I linearize, then again, that term B is the only term that comes in. And that term B is going to be obtained from the linear variant of my observation equation G. And that term B is going to be what? What's it going to be? The Jacobian of G. That makes sense to all of you guys, right? So very simple. And so I just stuck that in. That's just a standard Kalman gain equation. And so here I have my updated state, which is simply going to be the Kalman gain times. Observe that the only place where the linearization was used was in the Kalman gain, right? And also in computing the shrunk uncertainty, I minus k times b times the previous uncertainty. And so this is your entire extended Kalman filter. It wasn't very complicated, was it? This makes sense to all of you guys? How we went about it? Questions? R.O. Kalman, R.E. Kalman, Robert Emil Kalman. He was Hungarian, I think. I used to know his history, but don't ask me now, right? This was in the late 60s. But the person who actually made this whole thing really popular was Tom Kailat, who happens to be my friend's uncle. He was a gutsy guy. He wrote a 5-part paper on Kalman filtering for the IEEE transactions on information theory. And he titled the first paper Part 1. Now imagine the courage it takes to submit a paper to the IEEE transactions on information theory with a paper titled Part 1, considering the rate at which they bounce your papers, right? He went on to publish Part 2, Part 3, Part 4, and Part 5. He came up with this innovations process, and based on this work primarily, he was made an IEEE fellow before he was 25 years old or something, or maybe before he was 30. But went on to become the dean of Stanford. Some hotshot. So anyway, so this is the extended Kalman filter. You have an initial state value. Based on the state value, you're going to predict the next state value, right? By just putting it through the state equation. You have an initial state uncertainty. You use the linearized version of the state equation to predict the new uncertainty. Then you pass the predicted state through the observation equation to predict the state, the observation. You see the difference between the actual and predicted observations. And then you're going to use the linearized version of the observation equation to obtain your Kalman gain and the updated state uncertainty, right? That's this guy. That's how the uncertainty works out, right? So, questions? Any questions? Okay. Now, there's one key difference between the linear variant of the Kalman filter and the extended Kalman filter. In the linear variant of the Kalman filter, the Kalman gain was independent of your observations and the state estimates. Is that true over here? Yes or no? The actual state and the actual observations. The Kalman gains didn't depend on what you observed.
It totally depends. That varies as.
Over here it does, because the Jacobian depends on where you linearize the function, right? So in the extended Kalman filter, the thing tends to be a lot more unstable, because if your estimates for the states are off, your linearization is going to be poor, right? Where else can this fail?
Straight. changes.
Like this one, you're right. So you're assuming that the error increases slower than the Gaussian or the distribution falls off, right? If the error increases faster or comparably to how fast the probability falls off, then you cannot ignore the error. And so in these cases, like the figure to the right, you cannot actually, if you have functions with key structure, or if the Hessian of the function at any point is the eigenvalues of the Hessian are very large, which means it has very steep curvature, then this is probably not going to work very well. But for most functions, this works. I mean, we've been using EKFs for all sorts of things for a very long time. Now, questions? Just need a long enough nose. Yeah. So you have variants to this, variants of this called the unscented Kalman filter, the IEKF, the invariant extended Kalman filter. But then if you work through that, it might get all very, very simple. You just have to get the basic idea of Kalman filters into your head. Okay. So if you have no questions, this is the extended Kalman filter. If I assume that the noise distributions are not zero mean, you know how to correct for it. Would you know how to correct for it if these distributions were not Gaussian? You don't. Okay. So that's going to be the next problem that we will deal with. We've assumed so far that the initial state distribution is Gaussian. We've assumed that the probability distribution of the state driving term, epsilon, is Gaussian. And we've assumed that the noise in the observation is also Gaussian. Any and all of these can vary, right? Very often the Gaussian assumption just kind of works. So you can assume it's Gaussian, just keep chugging along. And even if it's not Gaussian, things kind of work. But then if you're a radar operator and you're trying to guide a missile or shoot down an enemy airplane in a dogfight, then the difference between a Gaussian and not Gaussian can have you blow your own pilots out of the sky, right? So then you have to begin worrying about how do I deal with non-Gaussianity of these distributions. So our issue was we assumed things were Gaussian and we assumed everything was linear. When things were not linear, we linearized them, right? So as a result, everything stayed Gaussian. Your initial state distribution would be Gaussian. Then your updated state distribution was P of S times P of O given S, right? And then scaled. So P of O given S was Gaussian, P of S was Gaussian, the product of two Gaussians was Gaussian, everything's Gaussian. And then what was the next thing we did? Over here, we multiplied two Gaussians and integrated one of them out. The result is still going to be a Gaussian, right? And then the next time around, we multiplied that Gaussian by yet another Gaussian, and it remained a Gaussian. Things were nice. The reason the entire thing worked is that the Gaussian distribution has this very nice property that it doesn't matter what you do with it, so long as the variables that are merged together are Gaussian, the entire thing is more or less going to stay Gaussian, right? So, but when any of these distributions is not Gaussian, then the results are not so happy. So let me go back and look at a very simple example. I'm going to assume that my observation noise, it's still, based on Gaussians, but instead of being just a simple Gaussian, it's a mixture of two Gaussians, right? So it's all Gaussian still. Nothing has changed, except instead of being a single Gaussian, it's a mixture of two Gaussians. What happens now? If I look at, so P of gamma is a mixture of two Gaussians, right? As a result, P of O given S, which is basically just the distribution of gamma with the mean shifted. is also going to be a mixture of two Gaussians, right? And so if your initial state P of S is a Gaussian, P of O, S given O is going to be P of O given S times P of S. So it's a mixture of two Gaussians multiplied by a Gaussian. So each of the Gaussians is multiplied by, each of the Gaussians in the mixture of two is multiplied by the Gaussian. So the product of two Gaussians is a Gaussian. So the result is now a mixture of two Gaussians, right? This is one update step. And then the next time around, let's just assume that P of ST given ST minus 1 is Gaussian, right? So we're going to multiply this Gaussian mixture by a Gaussian and integrate the second term out. So it's still going to end up with a mixture of two Gaussians, right? And then that mixture of two Gaussians is going to be multiplied by P of O given S the next time around. Four Gaussians, right? And so, and this was such a trivial change. One of the variables had was a mixture of two Gaussians, which is really not a very complicated distribution, right? And it's based off of Gaussians. And you don't need to get to 10 time steps before I run out of page space to show all the Gaussians you will need. So this isn't going to work. How do I deal with this? Any suggestions? Yes.
Anyway, do approximate as a Gaussian.
That was actually done by, the people did do that. You can try to approximate a Gaussian mixture as a Gaussian, or you can approximate other distributions as Gaussians. It's a very nice idea. Doesn't quite work because very often these are multimodal distributions and cannot be approximated as a Gaussian. But yes, that's a very nice idea. And indeed, that would be the first thing anybody would try, and that was what people tried.
Keep track of the approximate distribution. That's function. The big hit I'm getting an approximate histogram of that's a function. So keep track of the
Approximations, yes. Alex is kind of going the right direction, right? So let's see what we can do. First, I'm giving you a hint. But here's a question. Do you guys know how to sample from distributions? No. You don't?
I've never tried myself.
Okay. What do we mean by sampling from a distribution P of X? You want to generate random numbers such that if you generated an infinity of these numbers and plotted their histogram, normalized histogram, the normalized histogram would have the same shape as the probability distribution that you're sampling from, right? So, and there have been many algorithms to generate random variables from a variety of distributions, from uniform distributions, from category distributions. Do we know what a category distribution is? Discrete, right? Like the roll of a die, right? Or other things, right? Do you know how to sample from a category distribution? How would you do it? Suppose I have a loaded dice. How do you write a piece of code to generate samples from it? Mm-hmm. You guys know?
What is our source of randomness?
I'm just saying I have this dice and the probabilities, let's say I have a four-sided die, right? And the four-sided die has probabilities 0.1, 0.2, 0.3, and 0.4. Okay, so I want you to generate random numbers from this.
Computers are deterministic. I need a source of randomness to generate initial.
Okay, so you have a function called rand_n, which actually generates which generates uniform numbers between 0 and 1. So let's say, and there are many techniques. There's pseudo-random. It's unknown whether a truly random number generator exists in this universe, but you can definitely generate pseudo-random numbers. So a common trick is to take two very, very large primes, and then you keep working modulo and keep dividing, and the result is going to be a uniform distribution, right, over the second prime. But anyways, so given this, how would you actually generate a category distribution? You know, right? No? Okay. So here's what I can do. I can take this as 1, this is 0. And suppose I want to generate a random number, a 4-sided die with probabilities 1, 0.1, 0.2, 0.3, and 0.4, right? So I'm going to make my first bin with 0.1. The second one is going to be 0.1 plus 0.2, which is 0.3, right? The third thing is going to be 0.3 plus 0.3, which is 0.6 and 4. So this width is 0.1, this width is 0.2, this width is 0.3, and this width is 0.4. And now if I generate a uniform random number, the probability that it's going to fall in the fourth bin, what is it? 0.4, right? So if it falls in the fourth bin, I'm going to call it 4. If it falls in the third bin, I'm going to call it 3. If it falls in the second bin, I'm going to call it 2. I see a frown on your face. Okay, I mean, it makes sense, right? So very simple. So we know how to generate probabilities from a category distribution, right? This is how you do it. Now, how do you generate samples from a Gaussian mixture? There's no integration. How do you generate samples from a Gaussian mixture? Do we know how to generate samples from a Gaussian?
Yeah.
How?
You take the mean and take the standard deviation. You do the EXP thing. Forget the exact equation for Gaussian.
Okay, so here's the thing. So here's a very cheap way of generating a simple Gaussian with 0 mean and unit variance, right? You can generate 12 draws from a uniform random number, which generates a number between 0 and 1, and then average the 12 draws, subtract 0.5 from it, and you're going to get more or less a Gaussian random number with mean 0 and variance 1, right? But there are many other much fancier algorithms for generating random numbers which are pretty accurately Gaussian. So let's assume that I give you as a tool a magic function, which when called, so, y is equal to magic function. I just call it. And if I take a collection of y's, you're going to find comes from 0, 1. A Gaussian distribution of 0, 1, right? But now I want to generate a random vector from a Gaussian, except that the Gaussian has mean mu and covariance sigma, and this is a multivariate Gaussian. How can I use that first function to generate data according to this Gaussian?
So you have let's say data actions to generate different Gaussians.
So first I would generate d of these guys using the magic function, right? And then I'm going to multiply by sigma raised to half. The square root of the covariance matrix. How do you get the square root of the covariance matrix? How does one get the square root of a covariance matrix? You're going to take an eigen decomposition. So you would actually say sigma equals u lambda u transpose. It's a symmetric matrix. Everything's going to be real, and the u is going to be an orthogonal matrix, right? And so u lambda raised to half u transpose, which basically means that you take the square root of all the diagonal elements of lambda. This is going to be the square root of the covariance matrix. You can multiply it by itself, and you find you're going to get back the covariance matrix, right? So you know how to compute the square root of the covariance matrix. Easy. You can do this for pretty much any covariance matrix. So Now, so I can multiply this by sigma raised to half. The resulting variable is going to be a vector, d-dimensional vector with variance sigma, but the mean is 0. Right? And so how do I make it the new mean? And so this is going to give me a Gaussian of the desired mean and the desired variance. Everyone with me? Okay. So now I've given you the tools. How do I generate data from a Gaussian mixture?
Categorical and
First, I would have to choose the category distribution to select the Gaussian according to the mixture weight, and then draw a vector from the Gaussian using this procedure. Right? Everybody with me? So that's what we're going to do. Sampling from a Gaussian. This is in my, yeah. So that's the side trip. Let's get back to the topic. Here is the problem that we had, right? The problem was that we had a Gaussian mixture. We had a, if you have a non-Gaussian distribution, within seconds, within steps, 1 step, 2 steps, it's going to become impossible, even if every single term is perfectly tractable, which it often will not be. Right? So how do I deal with this? Based on the questions that I've just asked you, you should be able to get a guess.
Pick one of the Gaussians.
Pick one of the Gaussians. So here is the trick that we're going to use. And this is another crappy trick, which is often used. Okay? So suppose I have some probability distribution, P of x. And this is some odd shape. I'm just drawing something that looks vaguely Gaussian, but it doesn't have to be, right? And suppose I have some magic mechanism to sample values from this distribution. We know how to sample from a Gaussian mixture. We know how to sample from a Gaussian. There are ways of sampling from Laplacians. There are ways of sampling from all kinds of distributions. Just look up the literature, right? So if I'm able to sample stuff from this distribution, let's say I found sample like 50 samples. Where will those samples lie? Where will those samples lie? Where will they lie? In the middle. You're going to, what if the distribution were like this? Where will they lie? You're going to generally find more samples where the probability is higher and fewer samples where the probability is lower. Correct? And so if I sample, I'm going to get nothing off to the side. Okay? So if I were to think of each of these samples as representing a narrow bin in the space, right? If I generated 10 samples, and if I thought each of these samples is representing a narrow bin, where the bin is basically starts from the halfway point between these two and ends at the halfway point between these two, right? Then each of these, and let's say each of these bins has weight 1, area 1. Okay, so I'm going to say I have samples drawn from my P, and for each sample, I'm going to say P is approximated by the summation over my samples times a, let me call this step around sample I. Right? So what am I doing? I am taking this guy and I'm taking a step over here. This bin is going to be narrow, right? So it's going to be high. It's going to be touching the bin up here. This bin is going to be broad, so it's going to be low. It would be something like this, right? All of these steps now have the same weight. There is no weight with these steps, correct? But would this be a good approximation for this guy? Yes or no? Would this be a good approximation to the guy? As I add more and more samples, it's going to become a better and better approximation, correct? You're going to just, and now what has happened? I've taken this really ugly distribution that I began with, which could have had any shape, and converted it to a mixture of uniform mixture of steps. Each step is, as the steps are all different widths. That's how I handled it, right? Now I'm going to make one final approximation. So everybody with me so far? And so far we are doing just fine, right? We have not made any particularly crude approximations. They're statistically valid approximations. You with me? Right? So I'm going to approximate, say, this was my step approximation, and then I'm going to do something ghastly. And what is the ghastly thing I'm going to do? I'm going to approximate each step as a delta. Okay? And so I'm going to say summation over I delta S of Si, a chronicle delta. A direct delta, not a chronicle, right? Is it Dirac? Yeah. Whatever this. A delta function is a function that has zero width and unit area. So it's infinitely high and zero width. Okay, if I keep making the steps narrower and narrower and narrower, eventually they're going to become a delta, right? That makes sense, what I just did, right? And this is something that we often do when you sample a distribution. If you get really ugly distributions that you don't know how to handle, then a very common trick is to just say, I'm going to come up with some mechanism, some important sampling methods. There are millions of techniques for sampling from the ugliest possible distributions. Take the samples, approximate the distribution as a uniform mixture of deltas at these samples, and it's going to be a pretty decent approximation. Of course, you're sort of making the assumption that there's no probability for all the points between the samples. It turns out it won't really matter if there are downstream steps. So this is my discrete approximation to a continuous distribution. I'm going to be sampling a bunch of samples, and I'm just going to say that P of X is 1 over M times the summation of deltas. 1 over M to make sure, so because the deltas individually have area 1, so I need to divide by M, and if you take an integral of this distribution, it's going to be 1. Everyone with me? Questions, anybody? Yes or no? I just threw something particularly shocking at you. So there should be a question. If there's no question, then you're not shocked. If you're not shocked, then you're sleeping, right?
Debating example. So it's like it's about being something.
Mm-hmm. Yeah. I don't know. So let's see how this helps our lives, right? So are you all with me so far? Okay. So now, here's what happens. If I've got P of X is some horrible, ugly, nasty, hideous function, right? Then I want to do P of X times P of Y given X. Then P of Y given X has some form, whatever it may be. I've replaced P of X by a uniform summation of deltas, right? So then when I look at it, the approximation now becomes sum over all of the samples, 1 over M times the sum over all of the samples of P of Y given X, but Y given Xi. Observe that the left-hand side was P of X times P of Y given X, But because now we are only considering the samples that were drawn, that's going to be P of y given xi, where xi is the ith sample, times the delta at xi, summed over all of the samples. Does that make sense? Right? I'd point at it, except my candy cane has been stolen. You know, why would anybody steal a candy cane? Come on. I don't know. It was just outside. I mean, three of us stepped out and came back, and it was gone. Some CNU kid stole a plastic candy cane. I mean, the shame of it is galling me. Really. Right?
Please.
Are we so broke? Anyways. Go ahead. So, you guys with me up there, right? P of y given xi terms, delta x minus xi, right? Which is basically an impulse at xi. Now, if I integrate P of x times P of y given x, that's going to be, now the delta function has a property. If you integrate it, it's going to be 1, right? So P of y given xi times P of x. So what this integral really means is this, that if I've got, this is my delta function, it's just infinitely high and very narrow. If I integrate it, dx, this integral is going to be 1. Okay? Now, if I multiply it by some other function, f of x, the product is going to be 0 everywhere except over here. Right? So the integral of f of x times delta of x minus xi dx, I can write this as f of xi because the rest of the x's don't matter, right? Integral of delta, which is simply going to be f of xi. Make sense? Right. So what happens here? If I multiply P of x times P of y given x, that's going to be its y given xi. I'm not even sure why you need the w, so it's going to be just 1 over m, right? Okay, so now, so here's what we are going to do. We found that our state distributions can become very ugly. We're going to sample them. We will sample our state distributions and replace them by a uniform mixture of deltas. Okay? And so here is what happens. P of s, I'm going to multiply by, and this is my initial P of s. I'm going to sample it. It becomes a uniform distribution over deltas. The deltas will not be uniformly spaced. This is just for illustration, right? And then when I multiply this by mixture of deltas by P of y given O given s, then you're only going to be multiplying the delta at each point by P of O given that particular sample, right? And that is going to be P of O given SI is going to be different for each of the SI. So the heights now changed. The heights will sum to 1, but the heights have changed. That makes sense to everybody? Right. And so, and then the next step, I'm going to be multiplying P of S as 0 given O0 divided by P of S1 given S0 and integrating over S0, right? So S1 given S0 might be a Gaussian, for instance. Well, let's typically assume it's Gaussian, okay? So this is what happens. When I multiply this, then you're basically going to end up with a mixture of 4 Gaussians. Basically, you're going to say, so this has this property that, so this is a, if I have a mixture of 4 deltas of different heights, and then I multiply this distribution by, say, something of this kind, and then integrate it over x, the result is going to be basically this distribution positioned here, scaled by this height, plus this distribution positioned here scaled by this height, plus this distribution positioned here scaled by this height, plus this distribution positioned here scaled by this height. And so you're going to end up with that because this guy is high, and then maybe these two because they're low, and then that because this is high. And the sum of those four is going to be the resultant distribution. It won't have four, it's not going to be four independent distributions. It's going to be the sum of the four. It's going to be some peculiar multimodal distribution, right? That's ugly. And this whole business of things becoming multimodal is what was killing us, right? But what happens if I sample it again? Do we know how to sample it? First, you're going to choose a categorical value according to those four samples just above it, right? And then from that, you're going to choose sample a value from the distribution itself, which may be Gaussian or whatever else, P of, correct? And so this is going to give you a new bunch of samples. And so now this complicated, ugly distribution is now being modeled again as a uniform mixture of deltas. And then you get the next observation. So this is the predicted state distribution, right? And then when you get the next observation, this is going to increase the height, change the heights, right? And then the predicted state distribution for the next time is again going to be an ugly mixture, which you'd sample and go on. And so this is the entire process. This makes sense? Right? We handled ugly distributions. This is called particle filtering. This business of picking up samples is, these samples are called particles, and it's called particle filtering because it's Kalman filtering, and these are called particles because the samples are being called particles. There's a great deal of debate on how many samples you must choose. Obviously, if you have thousands of samples, you're going to be doing a much better job. But then sampling and compute ends up being very expensive. I once found myself in a meeting of radar engineers from IEEE who are having arguments over whether they should get 15 samples or 25, which is very peculiar to me because they work on these really critical problems. And I was working on a silly speech problem, and I was generating 250 samples. So, what is more important? But somehow that's what I thought was important. Anyways, so sampling results in a discrete uniform distribution. The update step updates the distribution of the quantized state space. What we are really doing is quantizing the state space at each step. And this results in a discrete non-uniform distribution. Then the predicted state distribution will be continuous. It's a mixture, but then you sample it again and it becomes discretized, right? So at any step, the current state distribution will not have more components than the number of samples generated by the sampling process. The thing never becomes more complex. This is the entire process. Everybody with me so far? And you don't even need to go through the math. The pictures tell you the story, right? So this is the standard Kalman filtering, extended Kalman filtering approach, where from the current state, you predicted the next state, then you predicted the next observation, got the observation, may have found the difference, scaled the error in the observation by the Kalman gain, and updated your state, right? Here, we're going to do something else. We're going to predict the state distribution. We're going to discretize the state distribution. You're going to get the observations, which are going to rescale the heights of these deltas. And then the updated state distribution is going to be continuous, which you're going to sample again, right? So, math. Anybody want to do math? No, I don't want to do math. Skip. I have lots of it. Okay. And if you feel like it, we can go a few minutes over. How many feel like math? Raise your hand. Okay, thank you. I don't feel like it, right? So, but let's see how this works, right? I'm going to run a simulation this time with a linear Gaussian model, simply because we know how linear models work, right? And so The state has a simple st equals st minus 1 plus epsilon, ot equals st plus some noise gamma, right? Noise, which I've called x. And I've generated a state sequence according to this guy. That's blue curve is the state sequence. And then I've generated observations where the xt is a Gaussian mixture. So just because I didn't want everything to remain Gaussian, if everything remains Gaussian, then I can just use my Kalman filter, right? So I made xt a Gaussian mixture, a mixture of 4 Gaussians in this case. And you can see what the observations look like. But we have some variance around the state, right? And our job is, given that patch of cyan, we have to determine the states. So there's the combined picture, okay? Now, at time 1, let's say I have an initial state distribution, which is Gaussian, right? I'm going to sample it, and that's my sample distribution. So then, that's my sample distribution at time 1. Then I use my first observation and rescale it. So that's what it looks like, right? So this is my updated distribution over the states after having generated the first observation. So this picture over here is showing that distribution on top. Is just showing the peaks. It's not showing the lines, right? And then the predicted state distribution is going to be continuous, right? Because I'm going to be placing my Gaussian at each one of these samples, scaling the height by the height of the sample and adding them all up. It just kind of looks Gaussian. It really isn't. It's a mixture of a grade 25 Gaussians or something in this case. This mixture of 25 Gaussians is now, it is kind of skewed in, if you can observe. It's not really a Gaussian, right? Then from this, I generate 25 samples, okay? And so those are my 25 samples. I obtain my next observation and scale all of these by the probability of the observation given that particular state. And the shape looks different, right? It's no longer uniform. So I plotted that out here at the second position at the bottom. And now I can predict my state at the next time again. This is clearly not Gaussian, right? It's a mixture of Gaussians which still has a bellish shape. And then I can sample from it. I get these samples. The next observation is going to change all their heights. I can keep repeating this process. Now, the key point here is that at each time, are you predicting a state now? Unlike the Kalman filter and the extended Kalman filter, in the KF and the EKF, we were actually predicting the state and we were predicting an observation, right? Are we actually predicting a unique state? We are predicting a distribution of states, right? The samples. So you're going to say the state can have one of these 10 values and the probabilities are blah. But is the state really going to be one of those 10 values? Probably not. So how can I use this to come up with a unique state value? I can take the mean, I can take the highest state, I can find the mode. There are different ways of going about it, right? And so, perfect. Thank you, Alex. And so, that's actually the mean, the top view. This is the estimated state. Sitting on top of the original state does a pretty good job, right? It's not going to be perfect, but it's not losing track and going haywire, which is the key bit. It will always recover. So this is actually, particle filtering is actually very effective where extended Kalman filtering or unscented variants or unscented Kalman filtering may not really be applicable. Potential applications, including tracking, they've used this a lot for edge detection in images in the past. And it turns out that because of the stochastic nature of the algorithm, they prefer to be, not use it. So most practical applications will still use EKFs. But these days, since our ability to model these distributions has improved a whole lot, what with the use of neural networks and such like, it's totally worth revisiting particle filtering. And so that little picture I showed you of the car running away yesterday, I think that was actually done using a particle filter. Again, it was a simulation. In real life, you don't want your car to turn around and go home because it encountered a truck, but still. So with that, it's highly dependent on sampling and you need a large number of samples for accurate representations. The samples, because of the stochastic nature of the sampling process, you may miss the mode of the distributions. Some distributions are just not amenable to sampling. So then in that case, you can use other techniques like importance sampling, for those of you who know what it is. And yeah, so prediction filters. We've looked at HMMs. We've looked at continuous state systems, Kalman filters, EKFs, and particle filtering. And any and all of these could actually have been used for your homework on predicting various time series, right? That said, I have never figured out how to stop something properly. So the best way to terminate things is abruptly. And so that's the last slide of my last lecture for this semester. Thank you, everybody. Any questions? If none, we are done. Good luck with the rest of the semester and the rest of your lives.